No dobra, jesteśmy tu, okej. Dobra, Mati, tu jest szerowane, okej. Pokaz slajdów, gdzie to się włączało? Czy jest Canva?
Nie, to jest Microsoft. Okay. Nie.
Nie, coś nie.
No tak, dobrze. Jakbyś mógł, możesz rozdzielić ekrany, tak żeby to mi się pokazywało. W sensie tu na laptopie.
To nie chcę nic mówić, ale jesteś taka upierdliwy.
Jest tak.
A nie może być to samo jak to samo?
No ale wtedy nie będę wiedział, co dalej mówić.
Jezu. Czekaj, to zrobię teraz. Display.
Wierzę w ciebie, na pewno ci się uda.
Nie, jest.
A masz jakiegoś przycisku, żeby...
Czekaj, czekaj.
Jak zrobisz, Mateusz, ten obrazek?
Już
Nie wiem. Nie.
Już rozdzieliłem tylko.
Ze zdjęcia.
Zdjęcia po prostu. Ale to jakimś narzędziem prostym fotosopowym, czy jak
No.
zrobił?
Dobra.
Ten.
To co mam pokazać? Dobra, okej.
No taki tak. Tylko jakbyś mógł to full screenem.
Się przenieść i zostawić.
11.
11. No to przycisk w ogóle. Zgłaśnianie jest mój FN, dobra, muszę wcisnąć.
No bo opcja. Taki.
Jezus, Maryśka.
Tylko tak.
Weź ty sobie sam to zrób. Przeglądarce trzeba wejść na full screen. Dobra, to już ty się będziesz o to martwił. I co dalej ci wisi ten komputer?
Mogę to zabrać?
Dobra, możesz, ale ja już tutaj nie panuję nad tym.
O, coś tutaj się jakoś dziwnie jest. Panie doktorze, pan tutaj odpowiedzialny za technikalia.
Jak się strzeliło w ogóle tak. Ktoś, który nie używał programu. On nie używał programu? Tak. Właśnie. I takie są skutki.
Zaraz się przykręcę.
Jest teraz w miarę prosto?
No teraz jest w miarę, to nie całkiem, ale okej. No teraz jest całkiem. Było lepiej. Tak jest prawie, jak jest proste, ale nie centralny. O.
Czy jest lepiej?
Jeszcze weź podnieś lewy bok. Dokładnie opisz prawy.
Tak?
No. A uwagi.
Zadzierać głowę, a będę widzieć ten omysł.
No właśnie, w końcu tutaj to się zna na rzecz. O.
Nie wiem co. Bo możecie pisać, tak?
Popika jest, nie jest tak, że...
Że jak się nie pisze, to jest...
Tak, ale możesz... O, nie,
Nie.
Dobrze, gdzie w ogóle. Wybiła 16.
We're waiting for Ilana a little bit and to start. Do that. I think. Today our speaker is Mateusz Mróz. He's our PhD student, almost finished. And today he will talk about searching planets in the OGLE database. Mateusz, floor is yours.
Thank you. Hello, everyone. Hello, everyone. As Mariusz said, I am Mateusz Mróz. I am PhD student over here. Hopefully on the final year of my PhD. And the seminar will be about all the work that I did throughout the PhD on the project that was focused on exoplanets in OGLE-IV data. As you just like history reminder, it's already almost 40 years after this 30 years.
More. May 1st.
Yeah, more than for 40 years by a few days from the paper that was actually that inspired the OGLE project and many other microlensing projects from Professor Bogdan Paczyński. He suggests for like large-scale photometric survey of the most dense fields of the sky in order to find microlensing events. Fast forward to the beginning of this century. As you probably know in this room, the OGLE project was extremely successful. And one of the main fields that consists of this success was the field of exoplanet detection. There are few methods of detecting exoplanets. Two of them out of major methods are photometric methods based on the measurements of the light of the star. And in both those two methods, OGLE was involved in first detections, first discover planets. Of course, it's microlensing technique. We were part of the effort of detecting first microlensing planet in the microlensing event, as well that we, Professor Galactic team, discover first exoplanet that transits its stars, first unknown exoplanet, unknown before. With 2010, OGLE entered into the fourth phase. Fourth phase was mainly started with the upgrade of the camera. You can see the camera over here in during its montage. over here is the inside of the camera, the 32 chips, and the camera already attached to the telescope. It was designed by Professor Rudalski. As I said, it was mosaic camera, and it's initiated the fourth phase of OGLE-IV. That was the biggest upgrade of the camera. It was enlarging the field of view of the telescope, filling almost the whole field of view of the telescope. That allowed to monitor much more stars and extend the survey to that include, OGLE-IV galactic bulge, Magellanic Cloud that were observed before, but also the galactic disk. As I mentioned, OGLE-IV was observed with high cadence galactic bulge. You can see over here the central field of the close to galactic center. They were observed a few times per hour throughout the first decade of OGLE-IV survey. And this allowed to gather enough data for after this next 20 years almost after the first discovery. I initiated the new search for transiting exoplanets in this data. I used the data. Thank you, show the screen. Sorry for I was not sharing the screen, but hopefully people online already saw those slides.
No jest.
Make a post.
W porządku.
Yes, everything is fine right now. Great. So I will fast forward. People can ask me a question of those first slides online. As I started talking, I choose the four most densely observed galactic bulge fields of OGLE. You can see actual images from the telescope. 4 fields of OGLE camera. I choose the most bright star in the main sequence. You can see on the with the green color, green point, the stars that I was checking for transit signal. Altogether, it was 200,000 stars that I checked. I used the algorithm that compared to the previous standard algorithm had a more natural shape of the transit instead of just box square. That's supposed to translate into higher signal. This algorithm also is more specific about the period and the transit duration that it tests for the signal. And here are the example light groups. So as you can see, the transiting signal, it's really small compared to the whole phase. Of course, many of you know probably that finding planets through transit method, the biggest disadvantage is this, that we have few cases of false positives. In false positive, meaning that some other type of object, not the planets. One of the false positives is, of course, it's called grazing binary. So we have stellar binary stars, but the companion of the object, the star, it's just covering its not whole surface cover its primary source. Therefore, the transit signal it's not reliable, telling us about the size of the companion. Other false positive signature, astrophysical one, is simply blending light. When you have blended light in the aperture, that transit signal is less deep as well. And of course, transit method telling us only about the size of the companions, meaning that small stellar companion in the size matter can mimic the transital signal. Of course, transitionally, normally we should perform rather velocity measurements to establish the mass of the companion. But as you probably know as well, the spectroscopic observations are expensive and not so easy to obtain. So people are using more probabilistic approach to determine whether the transit is false positive or not. I use pretty old right now algorithm of Vespa. It was created for Kepler discoveries. And this algorithm, based on the shape of the transit, based on the localization, on the galactic model, it tells us how big is the probability for this particular transit to be of planetary origin. And throughout all these candidates, I was able, using this algorithm, identify the most probable candidates for transiting planets. Here I have a sample of them. As you can see, many have different shapes, different durations, and on different periods. But it's possible to find many interesting candidates. Of course, due to the limitation of the ground-based survey, most of those candidates are hot Jupiters, with one exception over here. One transit that from the models I can guess that it's located in so-called hot Neptune desert, so deficit of the planet in the period or temperature versus size. One big advantage of finding the transiting planets is in typically microlensing fields, so in a galactic bulge, is that no other surveys probe the dense region of the galactic bulge, meaning that no other surveys are sensitive to the such galactic distances in the terms of transiting planets. You can see over here it starts. This is the sun location, and gray dots are known exoplanets in the galactic disk. Here you can see the feature over here. This is associated with the original Kepler field, so the direction that Kepler telescope was looking and discovered planets. Here you can see green dots. Those are microlensing findings, so in the direction of the galactic center, and those that are found from transiting planets are marked in red. So it's transiting method in the galactic bulge bridge somehow the findings for microlensing method. And this is really important because no other surveys can probe such a large scale galactic-centric distance, meaning that we can have more knowledge about how the galactic environment can shape the population of the planets. Now I will turn to the second part of my PhD, so the part that I focus more on microlensing planets. This is just small reminder how microlensing work. In the case of planetary system, we have the standard Paczynski curve that is symmetric, and then some small deviation from it that we can trace to the companion, planetary mass companion. First microlensing event that I analyzed, it was even from 2015. We have really small planetary anomaly. What is interesting here in this event is that it's rare case that it was sample whole anomaly and whole event was sampled with the survey data alone. You can see over here, this is the follow-up data, but actually to the build model, those data were not needed, meaning that it's really nice case for the exoplanet occurrence rates because it doesn't hang on the decision whether some event should be follow-up or not. In terms of the system over here, it was one of the interesting findings from microlensing planets, meaning that the companion was comparably high mass compared to the host. Normally, from the transits, from the Kepler discovery, people assume that higher the star, higher the mass of the companion. But microlensing findings are often contradicting this rule because we found it many high mass planets around low mass or even brown dwarf holes. Later in my PhD, I turned more into the more complex cases. This is the graphic interpretation of the most simple microlensing event, where we have one observer, one lens, one source, and the source and lens relative to each other move in the linear fashion. But of course, life is much more complicated, and we have many other high-order effects in microlensing events. First of all, we are sitting on the Earth, and the Earth is not stable. It's not fixed in the space. It's moved on its orbit. This is the effect called microlensing parallax. Here you have the comparison of standard, this dashed line, standard light curve, Paczynski curve, compared to one that incorporates the effect of the orbital motion of the observer. And it's incorporating the asymmetry in the light curve. The other effect that we can have, many stars are not single stars, they are in the binary systems. And with the microlensing, we can observe also the influence of the companion of the source star, so meaning that there are two source stars. And those can introduce some additional features in the light curve. We can also have, if the companion is, if the source system has companion, so meaning that it's moved on the orbit, that introduces the like mirror effect of the parallax. That's why the name Xaralab spelled backward. And it can introduce it like a wavy-like behavior in the light curve from the motion of the source. Of course, those two effects are connected, and we can have two luminous sources, both orbiting each other. And this introduces not only the wavy behavior, but also the signal from the secondary source. Of course, those visualization are exaggerated for the purposes of the slides. But in many cases, those effects are more subtle and less easy to distinguish between each other. This is the next microlensing event that I was analyzed from the 2017. This event was first published in Radek's works concerning white orbital planet occurrence rate, but the full analysis was not performed since from the preliminary results, the closed configuration was more preferred by the data. That's why I started working on it to establish full model. This event is interesting and particular because its light curve is complex and you can fit many different effects that are explaining the data good enough. Here you can see the two different models. One is the single source star on the parallel orbit. Second, as you can see from the trajectory over here, is simply two stars. And those effects, as I mentioned, they are the effects that are connected to the binary source system, and they traditionally, they are considered separately in microlensing works. And one of the cases is this event from 2010 that was first analyzed just based on the light curve, and the authors, Kurosawa, found only solution with the Xaralab motion. But then the follow-up high-resolution imaging paper analysis was published, and the authors from this work not only didn't find the solution from the first one, but also just from the imaging of the source, they established that the previous analysis underestimated brightness of the source, meaning that they consider only this model, instead consider both the orbit of the source and the binarity. But as you probably realize, that this can introduce a lot of freedom to the model. In the general approach to the modeling any orbit, you can parameterize any orbit using 7 parameters. Those are the 7 Xaralab parameters. If you want to consider additional source, you can just introduce the mass ratio, and then you, through the Kepler relation, you have both orbits established. And then you have traditional flux parameters in microlensing modeling. Those are the value that tells us from the gravitational microlensing, we get the magnification that introducing the effect introduces, but then we have to also model the original flux of the sources and the blended light. But this is a lot of parameters, and those are all the trajectory that are in 10 chi-square limit, all the trajectories that explain the data of this event. So as you can see, many different trajectories, many different orbits can reproduce the event, and this is actually problematic because it also influences the most interesting parameters like mass ratio of the planet. And when I start to model this and hit the wall of many unknown and a lot of freedom of the model, I start to focus on how those parameters relate to each other. We also, in microlensing, we introducing sometimes the finite source effect, is telling us how big is the source in the Einstein ring radius units. And all those parameters, they are telling about some astrophysical system. And those parameters are not independent to each other. This 4 parameters are bound by Kepler's third law. Those parameters, so the mass ratio, sizes of the sources, and their luminosity are bound by the symbol that they all describe one astrophysical star. And we know how those stars behave. We have the stellar evolution model. But of course, those models are not using the parameters that are traditionally used in microlensing. So to order to get the access to this knowledge, I introduced a few more parameters to the models. Maybe it's kind of counterintuitive to add more parameters in the problem that I complain that I have too much freedom in the models. But it actually works because using those parameters, the physical parameters that describe whole system of the source, I can use known stellar evolution tracks from the, for example, missed models. I use code that speed up the process, the Brutus code that using some neural network approximations to interpolate the grids. And then using those information, I create the star, the real star and its companion. And using those real stars, I know the fluxes that they produce. Normally in microlensing, those parameters are completely free and independent, and we feed them using linear regression. But in this case, I can incorporate this in each MCMC step. And this is really powerful because in each step of modeling, I can take this information and achieve the Einstein characteristic ring radius from 2 different sources and from 2 different sets of parameters. And this not only bind the whole model, that the whole model is on each step, it's astrophysically coherent, but also cut many unlikely solutions. Over here you have the models that use only 1 luminous sources. They could reproduce the data with the 4 orbital solution. On the other side, you have 2 luminous sources that could reproduce the photometric data with 23 orbits. And already on this step of creating from those orbits, creating initial step from further modeling, I cut off half of the model and the sampling resulted in 1 solution. So out of 24 different solutions I got using those reparameterization, I got 1 solution. And those solutions relate to each other, meaning that they are bound by orbital period that are equivalent of influence of 2 luminous sources of 1 luminous sources. And as a result, I actually got the full explanation of the system using this this model, and also as I was able to improve the estimates of the theta E Einstein ring radius by the order of magnitude. And this is full event once again. This is the main peak, and you have here over planetary anomaly. And what is important with this whole parameterization is that, as you can see, there are two different models of this event. One that is incorporating triple lens system, meaning that this signature is effect of two lenses, and this is the extra third one. Or the other solution is those solution that I was talking about with two luminous sources and the external orbit. And as you probably understood, that those solutions are completely different astronomical cases. In one, we have two planets orbiting one star, and on the other hand, we have one planet orbiting the same star. And to order to actually evaluate those models, we need to have knowledge if those solutions are astrophysical. And this is what I achieve using this reparameterization. And as a side note, this is really interesting case because if I will be able to get time for the rather velocity measurements for the object, it will be first confirmed or not Xarlap effect in the microlensing event. This is the finishing slide, more as my reflection about this, where the exoplanet science is right now. Many of you know, probably remember those years of 2014 and the beginning of the Kepler mission, how it changed our views on exoplanets and how big the revolution it was. And as you probably know as well, the Roman Space Telescope is coming and will be launched in September. And probably it will deliver same revolution, meaning that it's predicted that it discover more than 1,000 microlensing event, or the half of the order of magnitude that we know throughout the 20 years of ground space survey, and approximately hundreds of thousands transiting planets. And it's actually overlapped with OGLE fields. So we will get the access to the data, space quality data of many of our objects that were observed in OGLE. And that's it. And thank you very much.
Thank you, Mateusz. Sorry for the technical problems. Manage that. Do we have any questions, comments? So I was actually wondering if you add to the spectroscopy, to this parameters thing that you were mentioning, how that would help the spectroscopy and source. If you have like even one spectra that is moderate resolution.
So in principle, the two explanation is one that we have one source, and the other model is that we have two sources. Obviously, when I will get the spectra, I'll be able to distinguish those two cases. If I will see the lines from two sources, or only one, that it will, even without the radial velocity measurement. But obviously, when I will measure, if I will be able to measure the radial velocity signal, I can fix the Xarlap orbit parameters and then repeat the photometric model.
Then like only from a single, like if you don't see the secondary component, it doesn't mean that it's not there, because it may be too faint.
Yes.
So I was wondering if you could do something from that. I don't know, if rotation will help or something that can get.
Yeah, even like I said, the whole the point of this parameterization is that I was using the models of real stars, but obviously when I will measure I don't know, the metallicity, I can also kind of see, put some harder constraints of the mass and so on and so on.
Any more questions? Yeah, please.
So, maybe a silly question, but like, suppose there are some events that is detected by both microlensing and transit. And for those cases, is it a bit easier to break the degeneracy of the result that you mentioned?
So we don't observe the same system with microlensing and transit. That it's really, there's really low probability of doing that. It just the complementary of this method is that it's actually it's proved the complementary but not the same parameters range. So transit is sensitive for the close orbit planets, where the microlensing is more distant ones. The violet over here is sensitivity of the more or less transits, and the blue is the microlensing.
More? Do we have someone on Zoom?
No, I don't see any questions. So.
Yeah. So I don't see any more questions, so thank you, Mateusz.
Thank you.
Next week, something about AGMs, I think. Yeah, yeah. Okay. So see you next week. Thank you. Sure. Nie, nie, ale że bo ja na początku, tak, myślałem, jak mam